I usually don't step on toes, but that's what I'm...
As we think about tonight's agenda, I'd like to just talk about homework for a second and get any feedback that you might have encountered with the videos, with the homework assignments.
I have a question.
And go for it.
So when I went to download the Paradise Box
Okay.
file, it asked me if I wanted to buy a license. And because I'm here tonight, I'm like, I'm going to ask you, do we buy it? Do we sign up for a license?
No.
When I said no, it took me out. It wouldn't let me download it.
Had you established an account?
I have.
Okay, I have not seen that.
Okay.
And we're going to have to get together offline to pursue it.
Absolutely.
Okay. With that question, has everyone else successfully downloaded one of the project files?
Yeah.
All right, okay. We're going to have to get together and walk you through the steps of setting up the software.
Okay.
And we can do that in the afternoon one day.
Okay.
Okay. Has everyone begun to assemble a CNC blank for your project? Paul, I know Bob has.
I've got the wood.
Okay,
yesterday.
you're close. Chris, I saw some wood with your name on it.
Also, I've started.
Okay, all right. Then I expect that the individual projects will, in some way, for some amount of time, lag the class sessions, lag behind the class sessions. And to repeat a point I've made before, it's my goal to be in the wood shop almost every afternoon. So if there's any questions about a particular topic, like Sam, come in the afternoon, if we don't do it tonight, come in the afternoon, bring your PC, and we can sit down side by side and take a look at whatever software issue you're having. Or if it happens to be a manual woodworking task, if you need qualified on a particular machine for the next step, then we can take care of that during the afternoons also.
I had trouble with the second YouTube, those long ones that are on there, 40-minute and the other one's 50-something. That one said it wasn't available.
Okay, then send that note to me and I'll follow up. Quite often, if I used a video in a prior class and just brought it forward, they could have removed that video, and I'll need to look at that. I'll figure out how to replace it with equivalent content. Any?
The password to the Wi-Fi is Clubhouse. No caps.
Correct. The user ID and the password is the same.
Okay.
Makes no difference on the user ID, caps versus non,
Right. No,
Oh, you said all caps, didn't you?
No, I said.
All lowercase, yeah, all lowercase.
Lowercase, yeah, not lowercase. All lowercase. There we go. Looks like it. I must have fat fingered something.
Okay,
Okay.
all right. I guess it helps to turn it on. Homework assignments. Do you remember, Roger, do you remember which one you had difficulty with?
After that, the next page. It was the one that was 57 minutes long, I think.
That would be on the alternate homework list.
Okay, anyway.
Anyway, let's get together and
The first one showed you how to use the different components, the circle and all that other stuff. And then the
Okay.
second one I couldn't get.
maybe that was from session 1.
No, it was, I printed it out on that session 2 one. I thought I did. Oh, well.
Yeah,
Could have been.
because in the normal homework, I don't have a 30-minute plus. Okay. Any other homework issues? As we progress into this evening's content, we've got two objectives. One, we're going to go into the wood shop and we're going to demonstrate the CNC machine. And the demonstration is going to focus on the steps that you will go through to initialize the machine prior to beginning to cut in a project. Okay, that's tonight's demonstration. And then I expect that's going to take an hour. And following that, we're coming back and we're going to go through the discussion about toolpaths. And we're going to discuss the 3 toolpaths that are needed to cut the standard box. And then we'll follow up next week with toolpaths, and we'll talk more about detailed issues with any toolpath next week. I'll talk a little bit about next week's plans towards the end of tonight's session. I think I've said everything that's here. Setup issues, demonstrating how to set it up. Then we're going to talk about tool paths and a little bit of information about the tools. Prior to going into the wood shop, though, I'd like to walk through the steps so that you hear it here that you would take to set up the machine. And let's begin with power. I have it inside the right-hand open compartment of the cabinet for the CNC is an AC switch that will turn on both the controller for the SHARK HD-410, and it will also turn on power to the spindle. There's a transformer there that controls the power going into the spindle. So it's really just a simple on and off switch. I'm going to point to and show you the handheld pendant that we have for controlling the machine. Now, I'll tell you up front that we do not have it plugged in right now. Our primary tool for managing the machine is the PC that's there. I'm keeping the spindle in backup, and if something happen to the PC, I can plug the spindle in, or excuse me, the handheld pendant in, and control the machine. Now tonight there is a homework assignment, a video that's going to describe how to use the software to control the machine. And then in the alternate homework tonight, there is a video that describes how to use the pendant, and it covers all of the details of using the pendant to both set up the machine and to drive to accept a thumb drive and to initiate a cut from the pendant. And then I'm going to talk a little bit while we're out there about the spindle controls. I'll show you the variable frequency, the variable rotation of the spindle. I'm going to briefly talk about the router bits and point out where they're located, where they're stored. Now, several of us in the club have chosen to purchase our own router bits. Okay, just makes sense. If I keep them locked away, then I know when I pull that bit out, I know I can judge the relative sharpness of that bit based on how I've used it. We cannot do that with the bits that belong to the club. So they are available for your use, but should you run into a one that's not as sharp as we would like, just report it to me and I'll work on appropriating funds to buy another bit. Of course, if you choose to purchase your own bits, that's fine also.
Okay, if we were gonna buy our own bits, what would we buy?
Pardon?
What would we buy?
We'll cover that in detail tonight and next week. The calibration of the machine is rather straightforward. There are two home positions. There is what we refer to as machine home, and it's simply the front left corner of the 24-inch by 24-inch spoil board. Okay. And I'll show the tool tonight that you'll trigger to have the machine calibrate itself for machine home. And then there is a material home. This is a more flexible position that you manage. First of all, in your software. We talked last week about setting up the home position for your job, whether it be the exact center or maybe again the front left-hand corner of your workpiece. And I'm going to show the process tonight that we would use to set material home that will be the same location as you set home within your project file. After we talk about the homes, I'm going to focus for a few minutes on setting up the vertical calibration. We have a tool, a touch plate that's used, and I'll walk you through the routine for setting up the vertical home position. And we'll close with a conversation about securing material. We'll demonstrate that. I'll show you the latches we have to hold material in place. And then we'll talk about doing an air cut. And with that overview, let's go into the machine. Let's go into the room and focus on the machine. That's a switch for the light that's in the cabinet.
Okay, and the one down below to the right?
This is a switch to turn on the spindle power and also the controller for the CNC router. This is the controller for the CNC router, and this is the transformer that controls power going to the spindle. The transformer is really a frequency converter. It takes 110 volt power and converts it into a up to 400 cycle signal, and that 400 cycle signal through frequency drives the spindle, and the spindle is functional up to 24,000 revolutions per minute, RPM. There is a control here on the spindle. Now, that's the spindle running. Can anyone hear it?
Yep.
Barely. You get a lot of noise going on in this wood shop, and you cannot hear that spindle, and you have no knowledge that that's bits turning. We got some war stories later for the war stories. It is a variable frequency device, and I typically leave it at 17,000 RPM. Many of the files that you'll load have set the spindle speed for about 17,000. We'll talk more about that next week. There is a little dial here where you can make changes to it. I mentioned the pendant. The pendant is not plugged in, and it's a little bit dusty right now. I forgot to vacuum it earlier. I did vacuum the cabinet, but here is a controller. There is a port on the side where you can plug a thumb drive in, and it has all of the touch controls to both manage the machine and load a file and control a file being sent to the machine. Now, I think I've touched on everything on the left-hand column of that cell. Have I missed anything? We'll catch up later. Okay. As I said, the machine controller is here, and we have the personal computer wired to the machine controller. It is got a very secure password, PIN, 1121. 1121 will get you into the PC. It's set up for a single non-administrative user. The software that's used to manage the machine is called Ready to Control. Ready to Control. It's a little black icon on the bottom on the taskbar. A little black icon that will load Ready to Control. You'll also find it in the menu system, Ready to Control. It's initializing now. I will make it as large as I can. Okay. In the Ready to Control software, as it has initialized, it has exchanged information with the controller, and it takes control of the controller. You know that synchronization is complete when the arrows in the top right-hand corner of the screen move from a grayed state to the green and blue colors that you see. These arrows simply send a control to the device to move the gantry. And the gantry is the structure here, including the spindle itself. Using the arrows, I can move the gantry forward. I can move the gantry to the left or the right, or I can move it at a diagonal. Now, when I first initialized the software of the PC and the firmware of the controller has no knowledge of where the spindle is located within the machine. And the calibration that I mentioned earlier, its first step is to ask the machine to find machine home. Now the steps here is to first manually move the spindle where the cutting head, and notice I almost just touched there's no bit loading. And I will turn it off now. You'll hear it wind down. To move the cutting head within 4 inches of the left side of the machine and within 4 inches of the front of the spoil board. Okay. Now and then once it's in that position, you can use a home machine button that's currently in red, currently displayed in red, in home XY. You'll hear it moving. Now this is the controller searching for machine home. Eventually it's going to flip a switch, and it'll back away a ½ an inch after it touches that switch. He said it will eventually find the switch. He said, and I know this has absolutely never happened in the past. There was a little bit of a delay there, but it finally did its job. Let me do that again. Okay.
Joe, as you're lining that up, what do you use to indicate 4 inches from when you were lining up the spindle? What guides are you using to get within 4 inches to the left side, and are there any marks? Or?
There's no marks. There's no marks. When you're close to the machine, it's really easy to judge it. And if you are 4.5 inches away, it's going to go through 4 cycles to find one of the edges.
Okay.
If it doesn't find it within 4 cycles, it'll stop.
Okay.
Okay. And now it has found the home, and notice that the button here has gone green. And the green is a signal that I am in calibration for a machine home. Now, I didn't, I'm going to need a piece of wood later
Corner,
on.
it's finding the spindle itself.
A big part that has been activated.
Right, but the lineup of the spindle,
It's going to line up right here to this corner.
that's right.
The
The spindle is the one you brought to.
you can see the damage we've done to the spoil board when you get close to the machine. That's an ongoing issue. It happens, and periodically I will run a program that will smooth off the spoil board. Okay, and I can go down to another 1/4 of an inch before I will have to change out these MDF strips. Okay. But until I run that program, you will see the damage to the spoil board. And step by step, should you either drill into the spoil board for an alignment hole, and I talked about alignment holes last week, as you clean up after that particular job, if you can take another 5 minutes, find some filler, wood filler someplace, fill in that hole, that would help. That will prevent someone mistakenly choosing that hole in the future instead of the correct hole for his job. And you'll
These are the holes for the alignment pins.
right, yeah. And you'll probably see 8 or 10 alignment holes there that's already been filled in. Okay. Let's see, where was I? We were talking about, getting ready to talk about material home. Early on, I've chosen to begin to use the hold downs. I was going to talk about that last, but alternative here. I'm going to ask that everyone step over and take a look at what we've done. And pretend that board is very stable, but go ahead and walk around and get a close look as to how the hold downs work.
So you're placing them on each of the corners.
True.
Okay, it was placement, positioning, that's what
It's,
that is.
and quite often when you have a long piece like I do, and I didn't put it far enough to the right, I'm having difficulty on the left-hand side. And that's something you're going to work out with every job. You're going to place the material so that you can secure it. Okay.
So optimally, you would want to put your T-bolts down here and then down here. So that,
Repeat the question.
so you would want to place these bolts optimally within one of the guides?
You would want to,
So you'd
you
want
would
this
want
to
to
slide
place the
over?
material so that you could place a bolt
Right.
in between here.
Right.
That's,
Right.
okay. So now that I've got my material secured, and I know from the software where I need the material home to be, and let's just say it's this front left-hand corner, and that's an easy one. I'm going to either know the numerical location, and that's feasible based on the grid pattern that I've got in the spoil board. So let's just say that this particular point is horizontal 3 and vertical 3. I can simply specify 3 for horizontal.
So much for that.
Specify 3 for vertical. Notice how the colors changed when I went from horizontal to vertical. And remember last week in the, we were talking about X, Y, and Z, and there's a evolving color standard. This is an example of that. Now that I'm going to know to place it at 3-3, I can move to position, moving it to the 3-3 position. And for tonight, let's just pretend that that's correctly 3-3 at that position, and I can move down. Confirm that the bit is on that corner position. Then, right now, the machine knows that the spindle or the cutting head is at that 3-3 position. But I want to rename that to become material home. So I simply come here and I clear out the X and I clear out the Y, and now that is material home. So if I move anywhere on the machine, and to test that the machine knows where material home is, there is a control saying move to 0 and move to X, Y, 0, and the machine is going to move back to that physical 3, 3 position. Okay. Machine home is found by using a button here to calibrate the machine. Okay. Material home is determined by your job and where you have your job set for material home. And then plugging those coordinates, moving the machine bit to those coordinates, and then clearing out X and Y will establish material home for your job. Any questions? How bad did I screw that up? Terrible, huh? Terrible. All right. I told you we would talk about bits. And here are the the club's bits. These are the bits that came with the machine, and as one dulls, we replace the equivalent with an equivalent bit. And these are additional bits that we purchased for other jobs. You're going to find that there's a 90 and a 60-degree V-bit. This happens to be a 60-degree V-bit. And we're going to load it into the machine using the traditional collet. Okay, that is a collet. Pass it around. Okay. Very similar to what you would find in a hand router. Remember that the collet on any router is going to have normal clockwise threads, where when you screw the collet into the shank of the router device, you're going to be turning it clockwise. If you were looking down at it, it would be clockwise. The fact that we're looking up at it, it's clockwise relative to the spoil board. Okay, does that make sense? The maximum collet size for this spindle is 1/4 of an inch. And you know, with typical handheld routers, they can be much larger than that. We typically do not remove the collet. It's not necessary except for instruction. We load a bit into the machine using these 2 wrenches. A small one will grab hold of the shank, and then there's a large one for the collet. The shank itself is machined with a notch, where this bit, I think it's what, a 13 millimeter, will hold it. You can hand tighten the collet to the point where it will hold the bit in place. And then I tell people that not a lot of force is needed, and that's true. Clearly don't over tighten it. These are, so just a tug, simple tug will be adequate. Now, I've got the 60-degree V-bit loaded, and I need to remind everyone that the machine knows the horizontal and depth position of the bit right now, but it does not know the height. And the height is going to change anytime you change a bit. You're never going to be able to get the tip of that bit in the same location. Just not possible. So we're provided with a procedure that the machine provides for us to run through the Z calibration process. Now, I've taken a little alligator clip here and I've attached it to the shank of the bit, and there's a little touch plate that happens to be 3/8 of an inch thick, by the way. And I'm placing the bit where it's directly over where I've placed the touch plate. I'm going to bring this bit down to about here. Oh my goodness, it's 1/4 of an inch away from the touch plate right now. I'm going to ask the machine to 0Z with touch plate. Now the machine needs to be assured that the touch plate is beneath the bit. Essential. Otherwise, the force that's going to push down on your expensive material is going to put a deep gouge in it. These are powerful little motors. So the machine wants to know that the touch plate is beneath the bit. I'm going to bring it up and touch the bit. And if you notice, that control went from a dull green to a bright green. And that bright green means that I can go through and continue the process Okay, it found the touch place and it's backing up. So now the machine knows exactly where the tip of this bit is located. Okay? All right. I've covered securing the material. There's a variety of these little hold down, and if we lose one, I've got the file where you can machine another one. Find a piece of scrap wood, pretty easy, and get one of the exact length you need for your project.
Why don't you show moving the spindle to Z position to show how accurate it is?
Well,
You move it to XY, so moving to Z,
if I
exactly.
okay, sheet of paper, not a known thickness, but a very tiny thickness. If I were to position it under the bit, and I could say, close out of a couple of these dialogues, and I can say move to 0, and one of the options on move to 0 is move it to Z0. That's this option, I believe. Okay, now it's at Z0, and notice I can't move the paper. Okay, so I bring it up just to okay. Now it's set where the paper, you can barely move the paper. It was probably a centimeter or what is it? It was probably a fraction of a centimeter beyond 0 right now, but that's what the machine 0 is. Machine Z0. Okay. That's the process you were looking for. Okay. Now you've heard the presentation earlier about what we're demonstrating tonight. What have I missed, or what are you not going to remember when we leave here? We've covered the spindle speed. We've covered the fact that the spindle is so silent you got to be really careful. And you saw me demonstrate how my hand was close to the okay. Paul?
The pendant, is that what you called it? Does that do all the same things that you did with the computer, only you do it manually?
Exactly.
Okay.
Exactly. A couple of times we tried teaching the pendant and using it, but it's so much easier to use the PC. So much easier that we just put it in the background. But like I said, as a part of the optional homework, all of the details about using the pendant is available. Okay. What else? What else have we missed? Anything? Okay, well, that in mind, how do we do for time?
If you don't, one question just came to mind. If you don't use the pendant, you just put your flash drive in one of the USB ports on the computer?
I have a dongle here
Got it. Okay.
that we ran out of ports, so
I have one on my laptop, so got it. Yeah.
this is a laptop that was donated by a member, Paul Patch, and just for background, in its day it was a very good laptop, but it's not of a quality that's acceptable for Windows 11. So over the next year, we are going to have to figure out how to continue to use a laptop. And of course, donations, anyone donations?
Since that is now OWVA property, we give you replacement reserve.
Okay, with that, I think we've used almost an hour. Let me close by saying that as you progress with your project and you are ready to use the machine, you really don't have a key to get into it by yourself. So at that point in time, schedule some time with me or maybe one of the other people who are familiar with the machine could volunteer to help. And we will sit down and we'll go through and I'll have you do the step-by-step procedures that we've discussed. And I'll have you do it until it becomes natural to you. And at that point, I'll hand you a key. Okay, all right? Roger?
The bit there, can you push it up further, or is there a stop for it? The bit, can you push it up higher if you
Oh,
want?
yes, I could.
And then you could just,
There's a conversation we'll touch on next week on where that bit position should be. And the issue there is not a logical one. It's a physical issue as to how much force we want to put on the bit sideways. And the higher it is in the collet, the less total force is placed on the collet. Anything else? Okay, let's go back. Let's return.
I'll clean up.
What did I miss? I talked about the bit inventory. We demonstrated the inserting a bit. Chris is taking care of removing a bit. We talked about securing material. That's an art form. It's figure out what's best for your piece of material. Talked about the Z calibration. Material in machine home. Is there any issues there?
Yeah.
Material home,
Yeah,
based
sure,
on your
sure.
software
Yeah.
project. Machine home,
Yeah.
absolute.
The machine knows where it is.
The machine knows where it is. You just help it find it. Okay. And I guess I did prove the point that you can lose track that spindle is moving. Now that's, I know I forgot. The next time you're in the shop, look over on the right-hand side of the cabinet up top, and you'll see a heat exchanger. The spindle itself is water-cooled. And being that it's water-cooled, that's the reason it can run so silent. It doesn't have to move air and make noise. So, and there is a small flow meter, a wheel, in the tubing for the coolant that goes through the spindle. And you always want to look to see that meter is moving, that the wheel is moving. No,
Closed coolant
it's a closed loop. There's a fan, there's a radiator and a fan. It's not a high-speed fluid movement, but it's sufficient to keep it cool. Okay, that's probably the thing I missed during the demonstration, so please take a look. Oh, okay. I didn't hear any issues about material home versus machine home, okay? We'll talk more about that when we do the individual sessions. Tonight, we're dedicated to talking about toolpaths for the remainder of the session. Last week, we had a piece of material, a CNC blank in our hand. Everyone was here last week except Art. Art, okay. Chris, would you mind going into the project box where I'm keeping the material?
Paradise box.
Yeah, the new, where I've got the boxes stored, and there's a blank there that's been cut.
Okay.
When we're working, it does not have to be a two-sided project. We can easily cut a plaque or a sign single-sided. We don't need to do anything with the back of the material. When we design these boxes, if you don't want decoration on the end panels, and you don't want decoration inside the lid, we could easily cut these boxes as a single-sided project, okay? But because of the designs that I've described, yeah, it's a two-sided. So as we plan to run the material through the machine, there's decisions on what side we want to cut first. And then there's decisions along the way as to how we want to sequence the cuts for minimum bit changes and minimize the time necessary to do the job. So let's take a reasonable scenario. Here we are. The first side to be cut is the faces that are inside the box. And those faces inside the box are the alignment holes, because they have to be cut before you turn the material over with. The rabbit edge that we have at the bottom of the front of the box and the back of the box. Now both of these can be cut with what we call a 1/4 inch end mill. That is simply a 1/4 inch cylinder with cutting heads, typically spiral cutting heads, and the bottom is exactly flat. Okay? So we are talking about our very first bit, an end mill, 1/4 inch, upcut spiral. Okay? That bit will cut both of those tool passes, both the alignment holes and the rabbet. And then we've got to worry about the end decorations. V-bit. They are on the side of the ends away from the mortise that's going to hold the front, back, and bottom in place. Okay? Pretty straightforward. So the end decorations can be cut with a V-bit, the 90-degree equivalent of the bit that I used for demo purposes in the machine. Okay? And as I think about moving to the other side of the board, okay, I've got the decorations with the V-bit for the top, the front, the back, and maybe the chamfer that's on the front edge and back edge of the top. Okay, so with this,
Did you want the one that was cut out?
that's the one, yes, that would be better, but the box is also good. I can use the box.
Is it in your box also?
I think so. I hope so. Yeah, there's, for the box top, there's a chamfer across the front, a chamfer across the back, and then for the front of the box, there's a chamfer across here. So, and that can be cut with a V-bit, the same V-bit we use for decorations. Okay. Chamfer across the front, the back. Okay. The, so there are,
Conceivably, you could put decorations on the inside of the lid as well.
it's in the demo, excuse me, it's in the project files.
Okay.
And for any customization, like the date that you cut the box, this makes sense here inside, okay? The date it was done. Also, there's another opportunity for decorations that I often use, and it is on the back of the box right here. Faint, but it's there. Okay. Right in here.
Oh, yeah.
Okay. So, all of the decorations and the chamfer can be cut with the 90-degree V-bit, and then stepping forward, the any special decorations that you would want on the front. Thank you, Chris. The would be cut with the V-bit. I'm going to have to build this box pretty soon.
You made your tabs a little too weak on it.
So, repeating what I've said so far with the demonstration, the first side to be cut takes care of the alignment holes, the rabbets on the front and back edge, and any decoration on the end panels. And then turning the wood over, using the alignment holes, I can cut all of the decorations with the V-bit, and then switch the bit back to the end mill. And now the structure of the box can be cut. The structure would include the mortise for the front, back, and bottom on each side, and then the profile for the 5 components. So there are multiple tool paths, and let me name them. We have on the back of the box the alignment holes. That's a pocket tool path because we can cut a pocket with an end mill. We have the rabbet with the end mill. Switching to the V-bit, we got the decorations on, let's call it the first side to be cut, or what I'll sometimes call the back of the material. Switching on over to the side, continuing on with the V-bit, all of the decorations and the chamfer, and then going into the box structure. All of the decorations are cut with the V-bit using a V-carve profile. All of the alignment holes and the rabbets are cut with a pocket tool path. The decorations are cut with a V-carve tool path. And then the box structure, again, is cut with either a pocket tool path for the mortise or a profile tool path for cutting out the circumference of the 5 components. So I've named 3 different tool paths: the V-carve, the pocket, and the profile. And it's those tool paths that we're going to focus on tonight. Okay. Yeah, like took 3. The more efficient 3 instead of 5. Okay. We were beginning to talk about the details that are needed for a tool path. Now, generally, everything I speak of will apply to any tool path. And if it applies to only one, only a specific type of toolpath, I'll mention that. Okay, so any toolpath is going to need the identity of the vectors that toolpath will follow. There'll need to be a decision on the toolpath program that is needed for that particular path. And you've heard me mention the 3 programs that we need to cut the basic project for the class. There is the V-carve toolpath, the pocket toolpath, and the profile toolpath. You'll hear me repeat it at least 6 more times. Sorry. And then for the given program, okay, for that program, there are some details that program needs to know to correctly cut the toolpath. First one, the tool that it's going to use. Now, typically, a profile toolpath is going to be cut with a 1/4 inch end mill, or maybe a different size end mill. And typically, a V-carve toolpath is going to be cut with a V-bit. But that's not absolute. There are techniques where you can mix and match. Now, for the class project, it's pretty straightforward. The profile will always be a 1/4 inch end mill. Okay. The second, the depth of cut. Okay. For a pocket toolpath, for the project, the depth of cut will most likely be the half of the thickness of the material. More than likely. That could change. Maybe you don't need a full 1/4 inch. Maybe, for whatever reason, you want an 1/8 of an inch. Permissible.
Can that change within a toolpath, or is it set?
For a given toolpath, it's set for a given toolpath.
Okay, so if I wanted to cut deep and then cut not so deep, something to make a hash or something.
Those techniques would more than likely have multiple tool paths that follow each other. Okay? And we're going to talk more about that tomorrow. Tonight we're focused only on what's needed for the standard box. Okay? If I venture away from the standard blocks, throw something at me, please. Let's see. Depth of cut. All right. I mentioned the end mill. Okay. An end mill is, the bit itself is designed to cut perfectly flat along the bottom. And with making those machining decision for the bit itself, makes that bit inefficient to be used as a drill. Okay, so when you're using an end mill, you will typically want to ease that bit into the material by a sideways cut, a sideways angle cut to the depth of that pass. Okay. Also, the software needs to understand information about the vector itself, and any closed vector defined in the software is going to have a beginning point and an ending point, which is typically the same location, the same address. So the toolpath is going to need to know if it wants to start the cut at that start point, or whether it has the flexibility to optimize and figure out where it's best to start the cut. And here I did include one unique profile feature on my list. A profile cutout where I am cutting down to the spoil board surface. Okay. If I do not have some way of holding that material in place, okay, then of course it's going to shift around and possibly you're going to damage it. So that particular tool path has a provision for tabs that will be kept in place between the between the component and the spoil material. You can see tabs.
How do you keep when you're cutting the tabs? When you're cutting the tabs, how do you keep from going down to the spoil board and scoring it?
Long conversation.
Okay.
Now, but still it's a piece of data that everyone needs to understand. When you size your material, you've heard me say several times that the material needs to be exactly 1/2 inch or exactly 3/8 of an inch. Okay. Now, how good are we with a caliper? Can we, if we are good with a caliper and we have an exact 1/2 inch material over the entire CNC blank, then it really makes no difference whether I calibrate from the surface of that material or from the machine bed or the spoil board surface, okay? But once I'm not precise and I'm a little thinner than 1/2 inch, we are guaranteed to cut into the spoil board when I'm doing the profile cut, okay? So then hey, well, why don't I just always calibrate from the spoil board surface and I never have an issue. I never cut into the spoil board. Well, here I've got a little thin piece of material thinner than 1/2 inch or maybe thicker than 1/2 inch. So along comes a V-carve, and a V-carve when you are, and I'm going to talk about V-carve later. The V-carve says I'm going to calibrate from the spoil board surface. So I know I'm going to start that first V-carve and carve down to a 1/16 of an inch. But what if the material itself is a 16 inch less than 1/2? That V-bit is not going to carve the design that you want. We're faced with decisions, and most of the time we cut into the spoil board, like I explained earlier.
So get the wood filler when you're done. Get the wood filler when you're done and fill it back in. Got it.
Or plane off the surface quite often. The spoil board gets thinner and thinner and thinner.
That's why it's called a spoil board.
Exactly. Anyway, that's the issue there, and I guarantee you, you look and you'll see that where we've cut into the spoil board many times. But I haven't done that myself. No. Okay. Basic characteristics of a toolpath. We'll come back over and over again as we talk about individual toolpaths, and we'll see later on that there are other parameters we need to think about for some toolpaths. You've heard me use the word profile toolpath, okay? You've heard me use profile. And you've heard me mention an end mill, quarter-inch end mill. There's a little diagram here. Here, purple, there is a closed purple vector here. So to use the content to this purple vector as a component that we're going to cut out of a larger piece of wood, I can take an end mill, the blue circle here, and I can move an end mill around the circumference, okay, with the edge of that end mill touching the profile line, okay, a typical cutout, okay. Now, most router bits are designed to cut in a clockwise fashion. A router bit, a manual router bit, several here with woodworking experience. What are the ground rules for cutting an edge on a piece of wood with a manual router?
Well, I have to think about the physics now, but you don't want it to climb out of the cut. So you want to,
So
you're going to eat into it instead of chip it out.
Well, anytime you use a manual router, you're going to want some fence or that's protecting the wood from the router going into the wood. Now, the fence could be a part of the router bit itself. It could be a bearing that rides along the edge of the wood, or it could be a physical fence. But the ground rules are that you will move the router and the router bit in the direction where the bit is always cutting into the wood and dragging the router itself towards the wood by the rotation of the bit. Then using the fence to minimize or to eliminate that bit from going beyond where you want it to go, okay? Traditional router bit, okay? That is the, and with our router looking down, okay, the bit turning in the clockwise direction going down, that means that the direction to make a normal cut or a traditional cut, the bit would move this direction around. Make sense? Okay. It turns out that experiments over time, if I'm 180 wrong, the same point applies. The opposite direction, when you are doing a manual router, is going to bounce. You're going to bounce away from the material. We just don't have the physical ability to hold that router properly, cutting in that direction. But over time, the engineers have found through experiments that a device like ours is stronger at holding that bit, and they've proven with many cuts over time that you can achieve a cleaner cut by cutting against that pattern. And that's the direction of cutting the profile. So we can cut in the traditional direction, or we can cut in what's called an upcut direction. And quite often we will plan a project where a profile cut is in the upcut direction with the goal of getting a cleaner cut. So that's one of the issues we deal with in the profile bit. Now, also using a profile, as I described earlier, the software is going to recognize the dimensions of the cutting bit. It knows the purple line here, which is the parameter, the edge of the piece of material we need. And so he's going to draw a line, let's say 1/8 of an inch, away from the profile edge. And he's going to run the router 1/8 of an inch away from the material, which is going to cut exactly on the line that we need to cut. Okay? Now the software, of course, can figure all that out. But sometimes we don't need that exact edge along the... Sometimes, and a good example in this project box is the cut to provide the rabbet for the hinge. Okay? You'll see here somewhere that it's about 1/16 of an inch deep into the wood. So there, the profile is going to run away from the, and I think the red line here, no, I don't have an example here. So the red line, so a profile does not have to have a closed vector. A profile can follow any line you want it to follow. So if I draw a line a 1/16 inch away from the line I want to cut, and I run the a profile along this line, then I'm going to cut 1/16 of an inch into the material. Okay. And also, when we get into the details of the profile later tonight, there are parameters we can set within the toolpath where I can intentionally cut a fraction of an inch away from the line and cut the complete profile, and then I can back up and do a cut that will do a very, very thin cut to give you a cleaner edge along that for that piece of material. Okay, profile cut and some options about planning a profile cut. Questions? I know I've screwed up at least one of the points. Anything? Any profile cut? All right. We continue on. A pocket cut. Pretty straightforward. There is a closed vector. That closed vector defines the circumference of an area we want to cut in to the material. A profile cut, he simply says, I've got a 4-inch square. I'm going to design a tool path that's going to keep the edge of the bit away from the edges of the closed vector. And I'm going to make multiple passes until I clean out all of that material. Multiple passes. And V-carve. The V-carve tool path. Remove material. Okay, a V-carve tool path has to be a closed vector. Mandatory. And a V-carve is going to run a V-bit between two vectors to the point where the sides of the bit will edge along those two vectors. Now there's a little diagram here that attempts to explain it. Should I have a closed vector? Oh, here. And that is a closed vector, okay? Trust me, it is closed. The edges are represented by these two lines, okay? So I can look edgewise along the material. With this being the line on the left, this being the line on the right, the V-bit is going to come along and barely touch the line on each side. And if this is consistent, the same dimensions down the entire closed vector, it's just going to be a straight line coming down, a straight cut coming down, where the center is exactly in between those two vectors. But in reality, for some designs, we're going to have vectors. That's a closed vector. Okay. So what do we do? Because clearly the V-bit, because of the width here, is going to go deeper because of the distance between the two sides of the closed vector. So the program is smart enough to recognize that I can run the V-bit along this edge to a certain depth, run the V-bit along these edges to a certain depth, and eventually carve this out in such a way that I have, let's say, a flat bottom, okay, but I have V edges along the side, or excuse me, angled edges at the dimensions of the V-bit along the side. Now you will only see in these designs, this is all V-bit work here. It's all V-bit work. Same on the back. It's all V-bit work. Okay? And here's where the software has simply run the V-bit between two lines and the distance between the two lines is going to determine the depth of the cut. Okay. And if those lines are too wide apart, then there's another control that we can tell the V-bit toolpath to not go deeper than a certain depth. Okay, the V-bit toolpath.
Joe, you said it could make a flat bottom
Mm-hmm.
with a V-bit?
It's feasible if it goes over 10,000 times.
Okay.
But an understood issue, and later on when we get to the details, we'll talk about clearance options. And you can have a clearance option in a V-bit and use an end mill to get rid of most of the material, and then use the V-bit to go along the edge so that it ends up showing a V-bit. That's an example of what sometimes people will call a pocket in a pocket. I'm doing a clearance to create a pocket, and then there are provisions within the V-bit toolpath to carve in a pocket. So I can have a tool come along or a couple of tools come along and create the pocket with the V edges, with the diagonal edges. And then I can come along with another tool path and carve inside that pocket. Use the depth of the pocket as a starting point for creating the design. I don't.
So it's like cutting your grass. You cut your grass and then you use the etcher.
Well, yeah, that's a good analogy. A good analogy. Okay. Here's a little diagram that attempts to, with finer detail, make the point that I used the whiteboard for. And notice here, this being a 90-degree V-bit, I switched to a 60-degree V-bit and it's much deeper. And here's a 30-degree V-bit, and again, still deeper. I just wanted to bring this picture up quickly. We've seen it. Everyone has this loaded. Has this file loaded? Everyone. There is an icon I'm pointing to. Its function in life is to move the software out of the design and into the computer-assisted manufacturing mode where I can create toolpaths. Okay. Just flips the software. It moves the controls from the left-hand side over to the right. Lots of detail there. Let's break it down. I have some graphics here that remind the user of what the setup is. And the program that reports this is really a subset of the setup program that we covered last week. The icons tell us where the material home is. It tells us whether we're calibrating from the surface or the machine bed. Later on, when we talk about some three-dimensional carvings, there are other features that this program provides. There's an area here where the icon, or each icon represents a program to create a toolpath. A program to create a toolpath. There's an area here where the icons have general control over all toolpaths. And we'll touch on a couple of these tonight. And then there's an area here that identifies the toolpaths that have already been created. And of course, if I select one of those toolpaths, I can open up the dialog to make changes to it. Okay. Starting from the top left is the profile. Just the symbol itself shows lines around an object, and we immediately can say that icon represents a toolpath, a profile toolpath. An icon here that will call up the Pocket Toolpath program, Pocket Toolpath. And an icon here that will call up the VCarve toolpath. An icon here that will open up a program to run a simulator to show you what the toolpaths you have already created will do to a piece of material. Okay. There's an icon here to call up a program that will save a toolpath to a tap file, which can be transferred into the machine to actually cut that particular toolpath. And there is a icon here that is for the three-dimensional display. And I don't have the 3D display selected, but that is an icon where I can manipulate the three-dimensional display to look at a piece of material at a different angle, at different angles. Let's review for just a moment what ground we did cover tonight about the 3 tool paths. Let's go, and then we can go into preview the homework that we have for the evening. You know, we covered the 3 tool paths several times tonight, probably more than was fully needed for that presentation. The next item that we were going to discuss tonight was to look at the details of each tool path. The homework tonight is going to take you through those steps for all tool paths that the version 11 software was capable of. It's going to cover everything except the 2 new tool paths we have available to us now, and we will talk to those next week and the week after. What I have for the homework this weekend is a little video here talking about the basics of any tool path. It's going to cover much of the material that I talked about tonight. There's a video dedicated to the V-carve toolpath, and it's going to cover much of the material that we talked about here. And then there's 3 links here that's going to take you to Vectric documentation on these 3 tool paths. Within the past year, Vectric has improved their documentation, where there are many links built in the software, and they've reorganized some of the documentation where all of the information about a profile tool path is on one page. Now, studying the tool path details via documentation is a noble goal. I recommend it, but the intent of having the tool paths here is just to give you a quick reference to that documentation 6 months from now when you truly need it. You're in the midst of an issue and you need to read, so these links are available to you for that. And then there is a tool path right here, a generic tool path, a generic video talking about zeroing out a machine, the way we covered tonight in the demonstration. That is not directly associated with our machine, okay? But there is another video here that's going to cover the NextWave ready-to-control software, step by step, and it'll include all options of that software. And that is a video you should watch to completion. And then backing up, there's a video here. It's just a man talking about the variety of bits that are available. And the 3 that are the 2 bits that we'll be using are covered in that video. And last, there's a man first named Kevin out of the Midwest, made himself a millionaire out of CNC machines and using them to create product. Next week, and his video is really to prepare us for conversations next week. in a general topic we call feeds and speeds. Now, off the top of your head, can you tell me why router bits go dull?
They get hot.
Hmm?
They get hot.
What else?
Too aggressive, too fast through the.
Okay, that relates to too hot, but yeah.
Yep.
Abrasive material.
Running into a nail.
Yeah, a nail. MDF, by the way, is very abrasive material. Okay. The signs in the wood shop that previous officers put there saying, don't cut MDF on our machines, period. But that's not realistic. The signs are still there. There is an art we're going to talk about called feeds and speeds. The truly heat in most instances is the bane of keeping a bit sharp. And there's a theory that if I'm creating dust, I'm creating too much heat on the bit. And if I create big chunks, chips, that the chip itself is going to absorb some of the heat and take it away from the router bit. So there's a large, long conversation that we'll have over the next several evenings about fine-tuning the speed of the spindle, the RPM of the spindle, and the forward movement of the bit to obtain the optimum size chip to expend heat from and to minimize the wear and tear on the bit. Okay. Feeds and speeds, and that'll be, like I say, a topic for next week. Okay, that's our homework assignments. We're finishing 4 minutes early tonight. Making up for the 4 minutes late we did last week. So with that in mind, enjoy your homework and look forward to seeing everybody next week or in the wood shop in the afternoons. Okay.